I have to start with an apology, effectively. I got the impression earlier that you were all quite relieved to have brushed the AI stuff into a single obligatory AI session, but we're back. Maybe that's as it should be. I think you've probably all understood that the AI solutions are going to be inescapable. So I'm going to talk about Akida. Sorry, I should say that this was done with Gregor from Neurobus as well. Very quick overview. I'll talk about Akida a little bit, a simple use case, and then I'm going to slow down and talk about some hardware performance measurements. Alf told you all about Akida earlier on. I'm not going to add to that. I just want to insist on a couple of things. So it does exist in a physical chip already. There's 2 physical chips. The results I'm going to present are measured on these chips. But in addition to that, obviously, there's this really exciting thing for us to be included alongside the RISC-V and grain coming from front-grade Chrysler. And if I only achieve one thing in this talk, if I can tantalize some of you to think about the exciting things you can achieve, the doors that get opened to you by having a dedicated hardware accelerator alongside, then I'll have done my job, I think. I'm just going to talk very briefly about a simple use case to illustrate things. I'm not going to claim this is in any way state of the art. I just want you to know that this is not about a toy model. This is reasonably reflective of a workload that might be realistic. We've seen previously today the air ship detection type task. This is from a Airbus data set. There's big ships, little ships, some really little ships. But mostly what there are no ships at all, actually. There's only ships in maybe 20% of the images. With that in mind, if we think about a detection pipeline that we could use to work on this, coming from the data science side, if you want to do detection directly, yeah, we can do that, but it's going to be quite high cost. The models you want to do that, you want to use high resolution images, you want to use a larger model. So we might have something, this is from results, published results using a Jetson Nano. You're looking at maybe almost 3 joules per image that you want to process. We can do that a bit smarter at a system level. We could first, classification models tend to be much smaller, and we can run them at lower resolution. So I'm going to propose a model here that's going to run exactly that, lower resolution, and we're just going to classify images yes or no to having a ship. We're going to filter them that way. That's a scheme of it. This is the model I'm going to talk about. For those of you that know AI models at all, it's based more or less on a small mobile net. We heard earlier that these AI models tend to have a sequence series of layers. That's the layers here. They tend to have a large spatial area at the start, but few filters. And then by the time we get to the end of the model, we have a high number of filters, but a low spatial resolution. We can talk about the performance. Like I say, it's not state of the art, but we can get some pretty nice sensitivity to the ships. So far, so good. So just a simple case to illustrate this stuff. So I'm going to show first of all simple inference through Akida, and then we'll talk about ways that we can configure that to be a bit more efficient for particular targets. So this is just to make the connection between. Alf maybe mentioned earlier that a code is composed of multiple nodes and multiple neural processing units. So this is the mapping that we might see of this model. That's multiple layers. Each layer is going to get mapped to one or more of these MPUs. There's going to be quite a lot of MPs required for the early layers because of the large spatial volume coming in. The middle of the model, we get to small numbers. And at the end of the model, we need more NPs again for the large filter memory. So there's different constraints in different parts of the model. That's going to be a feature of these kind of things. So if I then run that through my Akida, this is on the AKD 1000. It's quite a big, it's an evaluation chip just to test different things. This is the kind of time it takes. Okay, I'm measuring cycles. I'm AKD 1000 is a 300 megahertz device. I'm going to scale it to 400 to compare with other stuff later. Anyway, it's going to take about 60 milliseconds per image coming through that, and you can see I've broken it down into the time per layer as a cumulative total here. Just another view of that here. This is the individual time per layer, and we can see that most time it's been taken in these middle layers of the model. And if we wonder why are those layers slow, it may be it's because we've not allocated many MPs to those layers. But I said we needed more MPs here for the filter memory or for the input buffer memory. In the middle, we've got few MPs allocated. So what happens if we allocate more MPs to that part of the model? Well, it's simple enough. The processing just comes down in a nice, more or less linear fashion according to the amount of MPs we've devoted to that. I've just doubled the MPs that I allocated to the center of the model. We brought the time down to about 40 milliseconds. So those of you that I think probably the sort of ideas that you guys think more about. Some of you are horrified at the minute that I'm, as this signal is coming through here, well, I'm using my NPs in series, which means a bunch of them are sitting doing nothing for a lot of the time. So I'm going to talk about some ways that we can make that more optimal. The first one, obviously, is in pipeline processing. We're going to process batches of images. In Akida, rather unusually for these things, GPUs are going to batch things in parallel. Here we're going to actually have a serial parallelization. We're going to, the first image comes in. While it's being processed in its second layer, we can start off the next image in the first layer. So it's going to be a serial pipeline. And once we've got a whole bunch of images coming through, we're going to be able to use all these NPs down our model in parallel, just by filling up the pipeline. If I do that, note the change of scale now. Suddenly we're down to under 10 milliseconds for the processing speed. We're up to 100 FPS for this case. And I can measure the power a bit more reliably in this format. We're at like 400 milliwatts for that configuration for the once I've loaded the whole model. That means we're coming in at something like 4 millijoules per frame. So that's like 3 orders of magnitude down from what we saw for the big YOLO V5 model. It's not a like-for-like comparison. This is a much smaller model. We're like an order of magnitude down on the size of the model, on the resolution as well. But we're getting an extra order of magnitude down, I think, from the processing in Akida here. How else do we optimize it? So here, what happens if we move to a smaller device? This is the Akida 1500. It's only got 32 NPs available. The full model doesn't fit. I'm going to have to process parts of the model at a time. So quite simply, we'll see in the mapping, we've got a second pass. We've split the model here. Sorry, one thing I should emphasize in all of these, with a single pass or in the pipeline, there's no once the model is loaded, there's no bandwidth of weights or intermediate values off the chip. Everything stays on chip the whole time. So the only bandwidth is sending the input image. Then you've got to recover a single value output from this classification model. In this case, now I've had to split the model, so I lose that. I'm going to have to, as I run the first pass and then the second pass in series, I'm going to have to reload the weights. So I've got weight bandwidth, but all of the intermediate values between layers stay on the chip the full time. So we see this pass. I can measure the timing in this again. And the key thing here is if I compare that to what I measured earlier on the other device, you can see the pattern of individual timing for the layers is very similar. And critically, this guy here, this is the one that we had to split just before. He's not any slower than he used to be. So we're losing nothing from having to, we've got no serious loss in throughput from the having to reload the weights. Okay, having made that conclusion that we're not losing out by reloading weights, well, the obvious thing is let's break up this model more. Let's allocate more and more NPs to each layer. So here I've maximized the spread of the model across NPs. Suddenly we're up to like 139 total. And if I do that, in this case, I'm getting, I've doubled the speed this guy was going at. We're down to 20 milliseconds, and we're getting much more optimal use of the available resources. Okay, I just want to close. I would point you to there's a poster from the guys at Front Grade Glass from Kenneth and Daniel. I've deliberately not talked about the event-based aspects. This case I've shown you is obviously it's using standard image frames. Alf emphasized earlier that Akida is an event-based processor, so we do get extra benefit in this kind of case. I'm keen to emphasize that actually these models, there's a lot of sparsity once you're inside the model itself anyway, so we do perfectly well on standard images. And that's all for me. Thanks very much.
you.